Throughout electronics and also in other areas of science, we have the familiar sine or cosine wave, but occasionally we want to see some other types of waveforms, and in this presentation we're going to look at how to derive a square wave, which is often used in digital electronics. By the way, I'd like to give credit to the videos from Khan Academy, which inspired me to do this video. This is a picture of Jean-Baptiste Joseph Fourier, and as the text says there, he was a French mathematician and a physicist who was known for a number of different things, including areas of thermodynamics and other areas of physics. But he's most well known for his infinite series called the Fourier series, which could be used to create a variety of different waveforms. It says that the infinite series is weighted sines and cosines. And what this means is that each term, whether sine or cosine in the infinite series, can have different coefficients, and it can have different arguments within the sine and cosine. So let's start with a picture called a square wave. This is a waveform that's often used in digital electronics where you have either on or off. And we're going to denote this as f of t. So this function, this square wave function, we will call f of t. And the hope is that we're going to be able to use Fourier series to create this waveform. As you can see, it has a period of 2 pi seconds, and that means that the frequency is 1 over 2 pi hertz. It also has a minimum of 0 and a maximum of 3. We could actually vary this and move this up and down on the y-axis, but for this one, to make it easier to calculate, we're going to use the minimum of 0. So here's a picture of a Fourier series. So f of t, we will say, is some constant value, a sub 0, and then we have a bunch of cosines added together. a1 times cosine t, a2 times cosine of 2t, plus a3 cosine of 3t, and so forth. And so we generalize that by saying a sub n cosine nt. Likewise, we have the sine values, b1 sine of 1 times t, plus b2 sine of 2t, and so forth, all the way up to b sub n sine of nt. And as I said before, the goal of this presentation is to find a way to determine these coefficients in order that we can write some expression that will be able to let us graph this picture. Okay, so before we start, in this presentation, we're going to need 5 different definite integrals, and they look like this. The sine of the integral from 0 to 2 pi, so we're going to be integrating across one wavelength of this waveform. The sine of some number times t dt, the cosine of mt dt integral, the integral from 0 to 2 pi of the sine of mt times the cosine of nt, and they may or may not be the same number, and we'll look at that as we go along. And then the integral from 0 to 2 pi of sine of mt times sine of nt. So here we're multiplying two sines together, and the arguments may have different values. And likewise, we have the same thing for the cosine, the integral from 0 to 2 pi of the cosine of mt times the cosine of nt dt. And in all the cases, m and n are going to be positive integers. So they will not be 0, they'll be positive integers. Also, we're going to need some trigonometric identities that aren't usually seen in most classes, and they are the sine of a times the sine of b, the cosine of a times the cosine of b, and the sine of a times the cosine of b. And as you see, this turns into this unusual 1/2 times the quantity cosine of A minus B minus cosine of A plus B for the sine of A times the sine of B. So we'll see those as we go along and see where we use those. Okay, so let's start off with the integral from 0 to 2 pi of sine mt dt. Okay, now to prove this or to figure this out, we're going to make use of the knowledge of the antiderivative. And what do I mean by that? Well, we know that the derivative with respect to t of the cosine of mt is going to be the negative m times the sine of mt. That's the chain rule in action there. And also the derivative of cosine is negative sine. So plugging that in to the sine of mt, what we do is we say, let's change that on the inside of the integral. We're going to multiply by a negative m, so that makes it like the expression above. But we can't just do that without doing something else on the outside. So we multiply the outside by negative 1 over m. So that makes the two sides of this equation equivalent. So knowing that the antiderivative of negative m sine mt is equal to cosine, we can simply say that the integral from 0 to 2 pi of negative m sine mt is just the cosine of mt. And since it's a definite integral, we evaluate that from 0 to 2 pi. So that's going to be the, again, negative 1 over m times the cosine of 2 pi m minus the cosine of 0. Now the cosine of 0 is 1, and the cosine of any number, any positive integer of 2 pi will also be the same value. If you think about a unit circle, that's going to come around to 360 degrees or 720 degrees and so forth. So in both cases, those are going to be 1. But 1 minus 1, of course, is 0. And so this particular integral will always be 0. And that's a valuable piece of information that we'll use later. So let's also look at the cosine mt, the integral from 0 to 2 pi. Okay, we're going to use the same strategy here. We're going to look at the antiderivative. Well, we know that the derivative of sine of mt is m times cosine of mt. Okay, so we use the same trick there, and we say that the derivative from 0 to, the integral from 0 to 2 pi of cosine of mt will be m cosine mt on the inside, but then we have to put a 1 over m on the outside to make it equivalent. Okay, so that becomes, again, like the previous example, 1 over m times the sine of mt, since the antiderivative of m cosine mt is just sine of mt. Okay, evaluate that from 0 to 2 pi. Well, the sine of 0 is 0, and the sine of any 2 pi times m will also be 0. So 0 minus 0 is 0, and we multiply out and we get 0. And it sounds like, well, we've got to nowhere here, but actually this will make that very complex expression we saw earlier, a lot of the terms will drop out. Okay, so next we have the integral from 0 to 2 pi of the sine of mt times the cosine of nt. And now we can make use of one of those trigonometric identities. And in fact, it's the third one that was shown on the previous slide. And it looks kind of like this. The integral from 0 to 2 pi of 1/2 sine m plus n t plus the sine of m minus n t and then dt. Okay, so that's from the trigonometric identity that we saw earlier. Now, there will be two possible cases here for this one and for preceding succeeding slides that we'll see. And that is, what if m is not equal to n? Okay, well, let's first off, let's break these two integrals up into the integral of a sum is the sum of the integrals. And so we'll pull, and also I'll pull the 1/2 constant out on the outside of the integrals. So we have 1/2 the integral from 0 to 2 pi of sine of m plus n t dt plus 1/2 the integral from 0 to 2 pi of sine of m minus n t dt. Okay, so for the first one, we notice that this is a non-zero integer. And from the earlier derivation, we saw that the sine of some number times t dt, that the integral is going to be equal to 0. Now for this one, this will also be a non-zero, so this will also be equal to 0. So we get 1/2 times 0 plus 1/2 times 0 is equal to 0. So for any cases where m is not equal to n, then this product of sine times cosine will be 0. Well, what about for m equal n? Okay, so we'll do the same thing. We'll look at the same sum of two integrals. The first one again will be a non-zero. The second one will actually be 0. So in the first case there, for the non-zero, we saw that that integral will be 0. And well, you say, well, what about the sine of 0? Well, the sine of 0 is also 0, and so that makes it very simple. And so this will be equal to 0. Okay, so that's when we multiply a sine times a cosine. All right, so now what about the sine times the sine of two possibly different values? Again, we'll use one of the trigonometric identities, and we'll look at the two cases where one of them is where the sine is, or the two values m and n are not equal. In this case, we have that picture just like the one we saw before. Of course, this is using a different trig identity, but it's in the same type of pattern. This will be a non-zero value. This will also be a non-zero value, and for reasons that we saw earlier, both of these will be 0. And so when m is equal to n, or not equal to n, then the values will go to 0. Okay, so what about for m equal to n? So we write down the same expression. Now in this case, this one will be 0, and this one will be non-zero. So the second term will drop out because that whole term will be 0. But the cosine of 0 is equal to 1. And the integral of 1 is simply the value of the variable, in this case t. So what we do is we say 1/2 t evaluated from 0 to 2 pi. Well, when we plug in those two values and subtract them, we'll get 2 pi minus 0, or 2 pi divided by 2, and that's going to just simply be pi. Likewise, we use for cosine mt times cosine nt, we use the other trig identity, which is this one. And again, in the same manner, we say, well, what about when m is not equal to n? We separate the two integrals. We see that that's a non-zero. That's also a non-zero. So both of these are going to drop out for the reasons we stated earlier. And for the case where m is equal to n, we separate the two integrals. This will be non-zero, and so that whole integral will drop out. And this one will be 0, and the cosine of 0 is 1. And for the same reasons that we saw earlier, um, the value of this integral will be pi. So to recap what we've just done, we say that if we have m and n where they are both positive integers, the integral from 0 to 2 pi of the sine of mt will be 0. The integral from 0 to 2 pi of the cosine of mt will also be 0. The integral from 0 to 2 pi of the sine of mt times the cosine of some different nt dt will also be 0. But in the cases of sine times sine, well, it will be 0 if m is not equal to n, but will be equal to pi if m is equal to n, or we can say that the integral from 0 to 2 pi of sine squared of mt dt is pi. And this is the same for cosine. When you have the integral from 0 to 2 pi of cosine mt times cosine nt, it's 0 if m and n are not equal, and it's pi if m equals n. And again, we find we want to see where cosine squared of mt, the integral from 0 to 2 pi, and we'll see that that's equal to pi. Now, a helpful visualization of that, if all of that was a lot of mumbo jumbo, let's take a look at just the sine for a second. Now you see here's a picture of the sine, and you notice that from 0 to 2 pi, we have part of the curve goes up, part of the curve goes below the x-axis, and when we add those up together, we have a positive area and a negative area, and since they're symmetrical, we find that the sine from 0 to 2 pi of the sine of x, of some value, is equal to 0. So that should make sense to you. But now for the sine of sine squared of x from 0 to 2 pi, you see that both of them are positive. Now it's not obvious that it's pi, but if you do the math, you'll see that that's true. By the way, both of these graphs and some of the graphs you'll see later on were taken from the great website called Desmos, www.desmos.com. I encourage you to check that out. So once again, the function f of t is an infinite series of weighted cosines and sines with their what we'll call Fourier coefficients, and I've color coded it there. So we have a0 plus a1 times all of the cosine terms, the a's times all of the cosine terms, and all of the b's times the sine terms. And remember, the goal here is to find a way to determine these coefficients in order to write that expression for the square wave. So we can categorize the coefficients, all of these coefficients, into really three categories. One is a0, which is right there. The other one is an, which is going to be multiplied by cosine. And then we have bn times the sine. So once we find a0, which is really a constant term, and then we can find an, which will define all of the other a's in there, all of the what we'll call the cosine terms. And then we can find all of the b's, which will give us the sine terms. So let's first find the a0 coefficient, that constant term out in front. To do that, what we're going to do is we're going to take that whole expression and integrate it from 0 to 2 pi. Wow, that sounds like a lot of work, but you're going to see something very interesting here. So we take the integral of ft dt from 0 to 2 pi, and we integrate that whole mess there. Now, how the heck do you do that? Well, first of all, notice this. You have that constant term there, and that's going to be easy to integrate because it's just a constant. So we'll get 0 to 2 pi. The integral of that's going to be a0t from 0 to 2 pi. We'll look at that in just a second. Then we're going to have all of the cosine terms. We're separating them out because remember that the integral of a sum is the sum of the integrals. And likewise, of course, we have all of the sine terms. Now here's where things become very interesting. Remember that the integral from 0 to 2 pi of a cosine term or a sine term is 0. So all of these terms right here drop out. They all become 0. And so we're left with that integral from 0 to 2 pi of a0 dt. Since a0 is a constant, we just pull that out, and we're left with just the t value there evaluated from 0 to 2 pi. And so we now know that that integral is equal to a0 times 2 pi. Or we can rewrite that as saying that a0 is equal to 1 over 2 pi times the integral from 0 to 2 pi of the function value. Now, at this point you may say, well, I don't know the function value. How am I going to do that? Well, have patience. You'll see that that becomes very, very simple in just a few steps. So hang on. So the next step is we have to find the an terms, all of the cosine terms. And the trick we're going to use here is we're going to multiply the whole thing by cosine of nt and then integrate. So we're going to say the integral of f of t times cosine nt dt is the following. Okay, so we have that whole mess in the square brackets times the cosine of nt there in blue dt. This becomes, well, here's the first term, the integral from 0 to 2 pi of a0 times nt dt. Then we have all of the cosine terms, and we have all of the sine terms. Okay, first of all, this term is going to be 0 for the reasons that we saw earlier. Then all of these terms are also going to be 0 for the same reason where we did a cosine cosine times cosine, where we had different arguments within the cosines there. So like for the first one, it's a1 cosine t times cosine nt. So we're going to say that if those are not the same, then all of those will become 0. So this term, which if you look carefully is going to be cosine squared of nt, is the only one that remains. So let's pull that up over here and look at that. So integral from 0 to 2 pi of an cosine nt times cosine nt is simply an cosine squared of nt. And so this is an times pi, if you remember that earlier derivation. And so the integral from 0 to 2 pi of ft times cosine nt dt is an times pi. Or if we write it in the terms of what is a sub n, we get this expression: 1 over pi times the integral from 0 to 2 pi of f sub n, or f of t, excuse me, times cosine nt dt. And again, once again, you're going to say, oh my gosh, it's gotten even more complicated because now we're multiplying f of t times the cosine of nt. How am I going to solve that? Again, be patient. You'll see that this becomes very, very simple. So now let's look at finally look at the b sub n coefficients that are on the sine terms. Okay, now in this case, we're going to do the trick. We're going to multiply everything by sine of nt. So once again, it looks like that. And so we're multiplying the whole mess times sine of nt. And so this becomes the integral from 0 to 2 pi of f of t sine of nt is, well, there we've got the constant term times sine of nt. We've got all the cosine terms. And again, of course, we've got all of the sine terms. So again, for reasons we saw earlier, this term is going to be 0. And likewise, all of these terms are going to be 0. So all of that mess is going to drop out. So it really simplifies. So when we derived those other expressions earlier, we found that we find now that is very useful, that a lot of those drop out or turn to 0. So now this is the only one that remains. And of course, you can see that it becomes sine squared of nt, which, if you recall, that becomes pi. So we set the original integral 0 to 2 pi ft times sine of nt dt equal to b sub n times pi. Or if we rewrite it as an expression for b sub n, we get that it's equal to 1 over pi integral 0 to 2 pi f of t sine nt dt. Okay, so we've got the following Fourier coefficients. The constant term is going to be that. The a sub n term is going to be that. And the b sub n term is going to be that. And once again, you look at this and you say, I don't know how to figure out the integral of some unknown f of t. I don't even know what f of t is yet. How am I going to do this? Okay, now I'll show you how that's done. So let's go back to our picture. So we have our picture of the square wave. And let's talk about the a sub 0 term. Well, first of all, that integral f of t dt can be broken up using the fundamental theorem of calculus by saying that the integral from 0 to 2 pi is the same thing as the integral from 0 to pi plus the integral from pi to 2 pi. So we've broken it up into two integrals into two different regions. So here's where it becomes really, really easy. From 0 to pi, f of t is simply 3. If you notice that the square wave, it's a horizontal line from 0 to pi, and the y value is simply 3. So it simply becomes 3, the integral from 0 to pi of 3 dt. Well, from pi to 2 pi, it's 0. And so that whole part drops out. So this becomes a very easy integral in saying that the integral from 0 to pi of 3 dt is simply 3t evaluated from 0 to pi, or simply 3 pi. And I think you can see that the pi's cancel out, leaving us with the fact that a0 is simply 3/2. Now look up at the graph, and you'll notice that the line of y equal 3/2 is simply the average value along the waveform, and that makes sense. So now let's find the cosine coefficients. So cosine coefficients a sub n are expressed as a sub n is equal to 1 over pi times the integral from 0 to 2 pi of f of t times cosine nt dt. Now I'm going to use that same idea that on the interval from pi to 2 pi, the integral, the area under the curve, if you will, is 0. So we'll just make that plus 0. So we have 1 over pi times integral from 0 to pi of f of t cosine nt dt. Okay? So now we say that a sub n is equal to 3. Now where does this 3 come from? Well, you know that all along the interval from 0 to pi, the function value is 3 because this is a square wave, and so it goes across, it's 3. And so we'll just pull that constant 3 out of the integral, and so that gives us the integral from 0 to pi of cosine nt dt. And now we'll use that antiderivative trick that we saw earlier. We're going to multiply the inside by n and then divide the outside by n so as to keep an equality. And so the integral of from 0 to pi of n cosine nt is simply going to be the sine of nt. Okay, so we have now 3 over n pi times the sine of nt evaluated from 0 to pi. Now, the sine of 0 is 0, and the sine of pi is 0, and so the whole thing is going to be 0 multiplied by 3 over n pi, and so that's simply 0. Okay, so now let's look at the sine coefficients. So the sine coefficients b sub n are expressed as b sub n is equal to 1 over pi times the integral from 0 to 2 pi of the function value f of t times the sine of nt dt. And again, we'll drop out the interval from pi to 2 pi since that's 0. So we're left again with b sub n is equal to the 3, which is the function value that we saw in the previous slide, over pi times the integral from 0 to pi of sine nt dt. And once again, we use our antiderivative trick by multiplying the inside, in this case by negative n, as you saw in a previous slide, and dividing on the outside by negative n. And so the antiderivative of that will be simply the cosine. So we have negative 3 over n pi times the cosine of nt evaluated from 0 to pi. Now, the cosine of 0 is 1, and the cosine of pi is going to be, well, it's going to be some value times n. There'll be n pi, cosine of n pi. So what are those going to be? Well, we actually have to look at this in two different ways. First, we have to look at the odd values of n. Okay, so for odd values of n, that would be 1, 3, 5, and so forth. The n pi would be 1 pi, 3 pi, 5 pi, and so on. And the cosine of each of those is going to be negative 1. So negative 1 minus 1 will give us negative 2. So multiplying this out, the negative signs cancel out, and we get 3 times 2 over n pi, which is 6 over n pi. Okay, so that's the odd values of n. Well, what about the even values of n? So that would be 2, 4, 6, and so forth. So what is the cosine of, for instance, 2 pi? Well, if you look at the unit circle, that comes all the way back around to 360 degrees, or 2 pi radians, and the cosine of that value, of all of those values, would be 1. So we have 1 minus 1, and in all cases that will be 0. And so when we multiply that out, we simply get 0. So now we have everything we need to know to figure out the function f of t for this waveform, this square wave that we've been looking at all this time. So in general, we have that a Fourier series for any waveform can be written as f of t is equal to a sub 0 times a sub 1 cosine t and so forth for all of the cosine terms a sub n times cosine nt plus all of the b terms times the sine, where the last term is b sub n sine of nt. But remember that all of the a sub n's are 0, and so all of those cosine terms will drop out. So for our particular case here, f of t is going to be a0 plus b1 sine t plus b2 sine 2t and so forth, all the way up to bn sine nt. So if we now plug in the values from what we saw in the previous slides, we get this, that f of t is going to be 3/2, that's the constant term, plus 6 over 1 pi times the sine of 1t. Remember, these are all the odd terms. So next we'll see, since that was 1, we'll see 3. So 6 over 3 pi times the sine of 3t plus 6 over 5 pi sine of 5t, 6 over 7 pi times the sine of 7t, we add that in, plus 6 over 9 pi times the sine of 9t, and so forth as far as you want to take it. And yes, of course, you on some of those terms, like 6 over 3 pi, you can reduce them, reduce the fractions. But I left it in this form so that you can see that it is a progression 1, 3, 5, 7, 9, and so forth. Okay, well, what does this thing look like when you graph it? What's it going to show us? Okay, so here's a representation of the first sine term. We actually have a constant plus the first sine term, and what do we see here? Well, this doesn't look anything like a square wave. In fact, it looks very much like a sine wave. In fact, it is a sine wave that's been pushed up a little bit and slid sideways a little bit. So this is not even close to being a square wave. But what I want you to notice is that I've drawn a horizontal orange line right there at 3, at y equals 3, and I've drawn a vertical line, that green line that's going up at a little more than 3. In fact, that's actually at pi. So that's the bounding box of our square wave. And what you should notice here is that the sinusoid is kind of centered over that box. In the first maximum that you see there is kind of centered in that box. And if you were able to see where 2 pi was, you'd see that the first minimum is also centered within that box. So that gives us some suspicions that we might be on the right track. Well, this is starting to look interesting. We have the constant term plus we have the first 2 sine terms. And notice that we have a little part that goes up and then a part that goes down, and then it repeats itself up and down and up and down. If we looked further along the graph, we would see this same shape repeating itself. So it's not quite a square, but it's getting close. Again, I'll mention Desmos, and it's a very useful website, and you can actually plug in any number of terms. They have a summation function in Desmos that allows you to graph these very easily. So let's look at Okay, this is 5 sine terms. So we have our constant plus 5 sine terms. And now you can see that it's starting to take a little better shape. I always look at these and it looks like teeth. Um, but so it's starting to look more and more like a sine wave. So there's a part that goes up very quickly, and then you've got some sinusoids at the top, and then it goes down, and you have some sinusoids at the bottom, and it repeats itself. Okay, and as we go along, this shape will get more and more like a square wave. So let's now look at 11 terms. So here's 11 sine terms, and you see that now it's getting even closer and closer to the picture of a square wave. Okay, now here's 50 sine terms, and I haven't written them all out because I wouldn't have enough room on the slide to see that. So we're starting to see a real square character of this waveform. But what you'll notice now is you'll notice what we call the edge effects, and in engineering they talk about edge effects on a waveform. So here are the edge effects. In the middle of the wave, it's pretty flat, but then when you get to the edge, you start to get these variations. Okay, look, you want to see what 100 looks like? It looks like this. So the edge effects are starting to they're still there, but they're less wiggly, if you want to call it that. And the nice thing about Desmos is all you have to do is you just plug in another number, and it will do that number of iterations for you. And here's 1,000. Here's what 1,000 looks like. And you see that it's very, very close to our original square wave. We still see the edge effects, but they're very minimal. Before I go further, I just want to show you how I generated the graphs in Desmos. When you get into Desmos, you go into what's called the calculator, and what you do is, for this particular function, you type in y equals 3/2 plus, and then you type sum, S-U-M, and you get this symbol. And then you fill in the limits 1 and 5, since there are 5 sine terms. You type in this expression, and when you hit enter, this is what you get. So the Fourier series can be used to create a variety of different waveforms using these weighted sums of sines and cosines. And these are very valuable, especially in electronics, digital electronics especially, but other kinds of electronics as well. And here's 3 examples. Again, we have the square wave, which looks like that. And here on this one, I haven't placed the minimum at 0. I've placed it at some negative value, and that can occur as well. You can also have what are called sawtooth waves. You can have triangular waves that look like that. So all of these you may see in an electronics laboratory. Well, I hope you enjoyed the presentation, and I appreciate you watching. And if you like the video, please like it and share it, and have a great day.